You clicked on this video because you want to understand PID control and you want to know how to tune it for your robot. But here is the harsh reality. The pursuit of a mathematically perfect PID tune is the single most common reason your hardware fails in the real world. By the end of this explanation, you will understand why the most robust systems are not those that eliminate error, but those that intentionally embrace a little bit of noise to save your motors from destruction. Most robotics tutorials teach you that the goal is to drive the error to zero. You adjust the proportional, integral, and derivative gains until the system tracks a target with microscopic precision. In a simulation, this looks like perfection. The graph is a flat line. The robot moves exactly where you tell it to. But simulations do not have friction. They do not have sensor noise. They do not have the microscopic backlash in your gearboxes. When you take a theoretically perfect tune and apply it to physical hardware, you are inviting disaster. The problem lies in how the integral term works. It accumulates error over time to eliminate any steady-state deviation. In a perfect world, this is beautiful. In the real world, sensors always have noise. A vibration, a temperature drift, or a power fluctuation creates a tiny error signal. A perfect PID controller sees this noise as a real deviation. It responds aggressively to correct it. Because the derivative term reacts to the rate of change, it sees the noise as a rapid movement and applies a massive corrective force. This creates a high-frequency oscillation that resonates with the mechanical linkages of your robot. Think of it like a car driving down a bumpy road. If your suspension is too stiff, every small bump sends a shock through the chassis. The car bounces uncontrollably. A PID controller tuned for zero error is the mechanical equivalent of that ultra-stiff suspension. It tries to correct every micro-variation in position. The result is that the actuators are constantly firing back and forth at their maximum frequency. This is not just inefficient, it is destructive. The cumulative effect of these micro-vibrations causes metal fatigue in your gears and overheats your motors. You might achieve perfect tracking for a few hours, but eventually the hardware will fail. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. This is why the industry standard is not perfection, but pragmatism. We are looking for a state of being good enough. A controller that tolerates a small, steady-state error is architecturally superior because it stops chasing ghosts. When you reduce the integral gain, you stop accumulating the error from sensor noise. You accept that the robot might be off by a fraction of a millimeter, but in exchange, you eliminate the high-frequency hunting that tears your machine apart. The trade-off is clear. You gain longevity and stability at the cost of a tiny bit of precision that your mechanical system could not maintain anyway. There is a deeper layer to this problem involving the concept of gain mapping. Many engineers assume there is a single set of PID constants that works for every situation. They search for the perfect Kp, key, and Kd values and stick with them. Research into PID control with gain mapping shows that this assumption is fundamentally flawed. The optimal control parameters depend entirely on the current state of the system. When a robot is moving slowly, it needs different tuning than when it is accelerating rapidly. When the load is light, the system behaves differently than when it is carrying a heavy payload. A single perfect tune is a myth because the system is never static. The dynamics change constantly due to friction, temperature, and wear. A static set of gains forces the system to compromise. It might be stable at low speeds, but unstable at high speeds. Or it might be responsive when empty, but sluggish when loaded. The solution is to make the controller adaptive. Gain mapping allows you to adjust the PID constants dynamically based on the system's current velocity or load. This ensures that the controller is always operating in a region of stability, rather than pushing the system to its theoretical limits where resonance occurs. But even with gain mapping, there is a gap in how we approach stability. Current literature focuses heavily on mathematical stability margins and optimizing gains to minimize error. There is a specific mechanism that is often overlooked. It is the intentional injection of noise. This sounds counterintuitive. Why would you add noise to a control system that is supposed to be precise? The answer lies in the physics of resonance. When a system is perfectly tuned to eliminate error, it becomes highly sensitive to its own natural frequencies. It locks onto these frequencies and amplifies them. By intentionally injecting a small amount of dithering signal, you break this lock. You introduce a controlled instability that prevents the controller from settling into a resonant loop. This acts as a low-pass filter for the control signal. It smooths out the micro-variations that the integral term would otherwise chase. The result is that the actuators move more smoothly, and the mechanical system absorbs unexpected disturbances rather than fighting them. This is not just a theoretical concept. It is a practical necessity for extending the lifespan of your hardware. Consider the difference between a system that chases every fluctuation and one that ignores the noise. The first system consumes more power, generates more heat, and wears out faster. The second system is more efficient and durable. In production environments, a controller that tolerates small errors is superior because it reduces the computational load and power consumption required for continuous micro-adjustments. The system becomes more resilient to external disturbances because it is not rigidly locked onto a single trajectory. It has a little bit of give, a little bit of damping that allows it to absorb shocks without transmitting them back to the controller. This brings us back to the core insight. The pursuit of a perfect PID tune is not just futile, it is dangerous. It leads to high-frequency oscillations that resonate with your mechanical linkages and cause cumulative hardware fatigue. The most robust systems are those that accept a good enough performance. They use gain mapping to adapt to changing conditions, and they intentionally inject noise to prevent resonance. They prioritize hardware protection over mathematical elegance. When you design your control loop, stop trying to eliminate every error. Start thinking about how to make the system durable. A little imperfection is the price of a long life. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.